So we're about a minute or so over. I will give a short introduction just to Zach introducing you, because I think part of what's really cool about this seminar is that Zach approached me and said that there was this faculty member doing research that he was really excited about and he wanted to know more about it. He wanted to push beyond the stuff he was seeing in the literature and so on and make that connection. And I think if you've been a faculty member long enough, having a student get excited in a way that they actually bring like ideas like this to you is really exciting. So I latched onto it and I was absolutely on board with Zach inviting him. And I am excited to have some new ideas that I wouldn't necessarily, as a physical chemist, have thought to invite to hear about. So Zach, please take it away and introduce our speaker today.
Okay, so today we're going to hear from Dr. Engle from the Scripps Research Institute in La Jolla, California, which is where he also did his PhD work. After which he went and he did a postdoc with Robert Grubbs, who, of course, most of you hopefully know, won the 2005 Nobel Prize for olefin metathesis work. He's won numerous awards, the most recent being the NSF Career Award and the Chemical Communications Emerging Investigator Award from 2021. His research tends to focus a lot on organometallic catalysis, specifically making and designing catalysts, figuring out reaction mechanisms, and coming up with new synthetic methodology, usually involving the difunctionalization of alkenes, as you can see we're probably going to hear a lot about today. And personally, I think it's very interesting work because alkenes are found all over the place. They're inexpensive. You can get them pretty easily. And so being able to do cool, easy, simple transformations to them can allow you to make complex products much simpler. But yeah, other than that.
Awesome. Thanks so much, Zach. Is everyone able to hear me?
Yes.
Yep, great.
Wonderful. Well, it's great to be with you. My only regret is that I'm not able to be with you in person, but I really am grateful to Zach for the invitation and Garrick for his help as well, putting this on. When you get an invitation from students, you can never say no as a faculty member. It's just so exciting to be able to share science and also meet new people and make those interpersonal connections. So I'm going to tell you today about what my group has been up to during the past 6 or so years since we first opened our doors here at Scripps. But before doing that, I'll tell you a little bit about my journey to get to this point. And I do so because, well, I know the audience, in addition to the faculty members in the audience, that the audience is filled with undergraduates and master's students who will still be finding their way naturally in this field and in their studies. And I think that sometimes when we're earlier in our educational careers and we see faculty members, we think that they had it all figured out the whole time and that their journey to this point was very linear, and that's certainly not the case for me, and I think for a lot of faculty members who I know. And so just walking you briefly through the experiences that I had that informed the choices I made during my education, and then how I ultimately got to where I am in terms of my career. I thought that might be instructive and hopefully a good jumping off point for the Q&A, which I'm open to field any questions that are on your mind, professional, educational, career planning, whatever. So with that, I would just say that even though you probably look at me and see a lot of gray hairs and think I'm quite old, I'm actually, it's not that long ago that I too was an undergraduate, and I consider myself to have been quite a clueless undergraduate. And if you don't believe me, I would direct you to this photographic evidence of my cluelessness. This is my organic chemistry study group, the three of us. You see, even though I have PPE on here in the form of these glasses, I don't even have it worn properly. But we were a bunch of knuckleheads, but very interested in organic chemistry. And in addition to having really positive experience in the classroom, I had two formative experiences at the University of Michigan, where I did my undergraduate work. One in in teaching, where my main mentor was the gentleman on the left, Brian Coppola, and he helped recruit me into this future faculty development program that he's run for many years. And this included activities like being a structured study group leader as an undergraduate. And then I was able to get an early research experience in the group of Adam Matzker, who's shown here on the right. I joined Adam's lab as a freshman and worked in his group for all 4 years, working on this interesting multidisciplinary project studying the self-assembly of monolayers in 2 dimensions, of physisorb monolayers in 2 dimensions that required using a battery of different approaches and techniques, including organic synthesis of the analytes in question, computational modeling, so you can see some of the computed modeled structures here, using an instrument called a scanning tunneling microscope, which actually allows you to visualize individual atoms and molecules when physisorbed to a highly oriented pyrolytic graphite surface. And for an undergraduate, this was an awesome project because I got exposure to all of these subfields of chemistry and got to think and reflect on what about it I actually liked, what really spoke to me and what didn't. And also I was quite amazed, and some of you in the audience will, this comment I'll make will maybe resonate with you, which is I had fully expected to come in as an undergraduate with absolutely no research experience. I mean, my only real professional experience is like refereeing 10-year-olds playing soccer. And I assumed I would just be washing glassware for a year, well, hopefully learning through osmosis. And within 2 weeks, Adam sat me in front of this scanning tunneling microscope and said, start collecting data. And you know, I broke my fair share of highly oriented pyrolytic graphite sheets, which cost about $500 a pop. But ultimately, I was collecting images like this, where we could actually see molecules with our own 2 eyes. And this was really formative in terms of how I thought not only about research, but about empowering young people in their pursuit of their education. But what I found really drawn to in Adam's group was the making of molecules, thinking about how that was done using state-of-the-art techniques, what the shortcomings were. And I wanted to gain more experience. And so I got to do that through a summer internship through the DAAD, which is the German Academic Exchange Organization, and they run this program called RISE, which stands for Research in Science and Engineering. It's an exchange where students at North American undergraduate institutions can work in Germany for a summer. And I got to work in the group of Professor Stephen Hashmi at the University of Stuttgart. And the project that I worked on was in homogeneous gold catalysis. So this was the first opportunity I had to transition from doing organic synthesis as kind of taught at the undergraduate level to doing homogeneous catalysis. And I thought this was just amazing because you could take small amounts of these transition metal catalysts and they would completely mutate these organic starting materials into completely foreign looking structures through bizarre mechanisms that I knew nothing about at the time. And I thought this was so captivating to me. I had to continue learning more and educating myself in this area. And I also had a wonderful cultural experience, as you can see on the left here. This research internship was in 2006 when Germany was actually hosting the World Cup. So here we are at a public viewing site. You can see I'm the only one not dressed up in traditional German colors. And here I am hiking in the Austrian Alps. So I think this really drew me to not just pursuing my education seriously, but in thinking about the connection between research and international collaboration, which has been a theme for me as well. So after I graduated, I wanted to go back to Europe and learn more and broaden my experience. So I was able to get a Fulbright scholarship. I worked in a different lab in Germany at the Max Planck Institute with the gentleman on the left, Manfred Raetz, and then spent the summer after working at Stockholm University because Professor Raetz had a collaborator, Jan Beckvall, who he was willing to share me with for a couple months, so I could get different experiences. And between these two labs, I learned about palladium catalysis and biocatalysis, directed evolution, which was being done actively in both of these groups. And so this was a really wonderful platform for me, and really solidified my interest in pursuing a PhD, which I still wasn't sure about, believe it or not, even after all these experiences, until getting there and kind of dedicating myself full time to research for an extended period. So then during my PhD, I enrolled in this unusual program called the Skaggs Oxford program, which is a 5-year program coordinated between Scripps Research, where now I'm a faculty member, and University of Oxford. I worked with 2 faculty members, Jin Kuan Yu at Scripps and Veronique Gouvener at Oxford, and also applied for and was fortunate to receive a number of different predoctoral scholarships. I'd be happy to answer questions about this if anybody is curious. The NSF Graduate Research Fellowship and the DoD National Defense Science and Engineering Graduate Fellowship. And just to summarize my PhD research in like 2 or 3 slides here, in the U Lab at Scripps, I worked on this technique called CH activation, where you using a transition metal catalyst, you can access organometallic intermediates through CH bond breaking, and turn on reactivity for traditionally unreactive starting materials, and enable them to participate in some of the classical cross-coupling type transformations that now are ubiquitous in organic synthesis. So we can use this technique to streamline the synthesis of target molecules. We can use it as a technique in diversity-oriented synthesis for taking a bioactive lead compound. Here's an example where we take a Celebrex derivative and then perform CH activation at different sites to create new analogs for bioactivity assays. And then at Oxford, I kind of changed gears and worked in the area of organofluorine chemistry, thinking about new ways to make CF bonds from cheap and expensive starting materials. And Professor Gouvener, who I worked with, is one of the leading experts in this field. And organofluorine compounds have a number of different applications across different sectors of modern society. But one of the limitations or issues in this area is how fluorine is typically incorporated into organic small molecules. And as this field moves forward, one of the things that is needed is new methods that can take fluorine as you find it in Mother Earth as fluoride anion, and use that as the fluorine building block. And the strategy that we took was to develop this hydrogen bonding approach to control reactivity of fluoride anion. And we actually developed this series of reagents that are now commercially available. So if for some reason you want this adduct TBAF bisphenol, you can buy it. But these are shelf-stable stable fluoride sources that do not absorb moisture from the atmosphere and can be used conveniently in organic synthesis. So as you can see, I had a diverse set of experiences coming out of my PhD, and sort of the last training experience I had was with the now unfortunately late Professor Robert Grubbs at Caltech. Grubbs shared the Nobel Prize, as Zach mentioned, with Dick Schrock and Chauvin for the development of olefin metathesis as a synthetic method. I think, one of Bob's enduring legacies is the 20+ years of catalyst development research that went on in his group. And even though this is quite well established technology these days, there are still actually a lot of things that the current catalog of catalysts that are available cannot do well. And so one of the problems I worked on was designing tunable ways to initiate catalysts for different applications in materials chemistry as well as in organic synthesis. So building out the toolkit with a tunable initiation profile. And then in 2015, I started my independent career at Scripps, and I think Zach set up really nicely what our research program has focused on. You can get the sense that through these experiences, I was gaining an appreciation for the power of catalysis and for using catalysis to make functionally important molecules. And when we think about what types of molecules are functionally important, I always just get back to structure, paying attention to the structures of compounds that are of use in modern society, including human therapeutics, and thinking about what types of structures, structural motifs, what types of substructures, what types of functional groups these functionally important molecules contain, and then asking the question of how are they made using state-of-the-art methods, and could we potentially innovate to streamline their synthesis, enable them to be prepared from simpler starting materials, or in ways that are more modular, more flexible, more sustainable. And so in this context, my group and I began thinking about this functional group motif that's called vicinal functional groups, meaning two carbon atoms, each of which has one functional group hanging off of it. And this type of motif is really a fundamental building block of any three-dimensionally complex organic molecule. I've shown just arbitrarily a couple, I've shown here 3 arbitrarily selected compounds that exhibit this type of motif. These are all anti-cancer compounds. And some of these actually, as organic chemists, we know how to make pretty well. So for example, you see on the right a trans 1,2-diol, and just drawing on your knowledge from undergraduate organic chemistry, you would think about an epoxidation and then a hydroxide mediated ring opening as a way to make this. But if we dig deeper, there are other types of motifs. So here's a 1,2-aryl carbonyl motif that there aren't great ways to make using state-of-the-art methods. And so the question that we asked, really, from a 30,000-foot view, is could we access all possible vicinal functional group combinations from a common class of starting materials, namely alkenes? And could we identify the appropriate catalytic toolkit, metal catalyst, ancillary ligand, et cetera, to be able to do this in a really modular, user-friendly manner where you can really pick off the shelf and mix and match different components and stick them onto the target alkene starting material with Mr. Potato Head-like precision. So a finite number of building blocks, but mixed together a near infinite number of combinations, that certainly would be an empowering tool for medicinal chemists as well as for other types of applications. And so if we think about this genre of reactions, which are alkene difunctionalizations, and some of these I think should look very familiar to everybody in the audience. So one of the classical transformations that we learn as undergraduates are 1,2 dihalogenations. So the example I've shown here is a 1,2 dibromination. And if I ask you to think about what the mechanism is for this, maybe this is too close to home. I don't know when you took your organic exam. Hopefully this is you have enough distance from this that you're not like having PTSD from a recent exam. But if I asked you what the mechanism for this is, okay, we'll get to that. Sorry. So we'll talk about the mechanism for this. But then what we want to do is to kind of move beyond the set of known transformations into reactivity space that looks much more bizarre and much more complicated to execute potentially. And this really motivates us thinking deeply about reaction mechanism. So the mechanism for a 1,2 dibromination, if you drew this on an exam, then you would get 0 points and you'd get a talking to from the professor, because this is wrong. You have something that's fundamentally should raise alarm bells as an organic chemist, because you have an electron-rich bromide anion attacking a electron-rich alkene, and this is basically like having the wrong ends of a magnet meet. You have too much electrostatic repulsion. This type of addition would not happen. The mechanism commonly invoked instead is the one shown here, where the molecular bromine serves first as an electrophile, transferring Br plus to give a bromonium ion. And the formation of the bromonium ion is really what activates the alkene for addition of the nucleophile, in this case, bromide. And that thus delivers the 1,2 dibrominated product. And the key point here, and that I want to, if there's only one takeaway here, it's in terms of the underlying mechanisms of the reactions I'm going to show you today. It's this slide. In a 1,2 dibromination, as well as other reactions that I mentioned, like for example epoxidation and then hydroxide mediated ring opening, the alkene activation step, the part where the alkene is converted into reactive electrophile, is the same as one of the C heteroatom bond forming steps. So if we want to get away from this paradigm to be able to introduce any two groups that we want, we cannot have the activating step and the CC or C heteroatom bond forming step be coupled together. They need to be decoupled. And so that gets us to thinking about the transition metals and their reactivity, which in many ways is alien to the main group elements. They interact with main group elements in very different ways than main group elements interact with one another, owing to the presence of their energetically accessible d orbitals. For example, transition metals, when coordinated to alkenes, can engage in this phenomenon called pi back bonding, where they can accept electron density off of the alkene and render it electrophilic. That's what I've shown here. So coordination of a metal in the appropriate oxidation state can effectively umpole the alkene, switch its polarity from being electron-rich in character to electron-deficient character. Now a nucleophile can attack. You can almost think of this as like a quasi-bromonium or quasi-epoxide. The nucleophile can attack, that forms a carbon nucleophile bond and now a carbon metal bond. And it turns out that these types of carbon metal bonds possess reactivity such that they can engage with an electrophilic component in solution. I've just abbreviated that as generic electrophile E, and form a new carbon electrophile bond. So now the key point is that we have this metal mediator that we want to use catalytic quantities, because this gets liberated at the end of this reaction. It can keep finding another molecule of alkene and spin round and round the cycle. We've decoupled the alkene activation step and the bond forming events. And so this, we thought as a team would be our roadmap to develop very general 1,2 difunctionalization. And then the question is, what type of metal would mediate this type of alkene activation? Where would be a logical starting point for building out this toolkit? And then what are the problems that you need to solve to make this general and useful? And so let's address this one question with a quick trip down organometallic memory lane, or a quick jaunt into the history of the development of the field of organometallic chemistry. So what type of catalyst would be useful for enabling the pi-Lewis acid activation, the electrophilic activation of alkenes? Well, this goes back to really the middle of the 1900s, or middle of the 20th century, maybe I'll put it in those terms. And in post-World War II Germany. And there, during this time, between the 50s and 70s, many of the key foundational principles of the field of organometallic chemistry and homogeneous catalysis were established. And they were established in this context of thinking about taking petrochemical feedstocks and converting them into useful products. So one of the processes that was used on industrial scale back then was conversion of calcium carbide to acetylene, and then conversion of acetylene to various building blocks, as shown here, vinyl acetate, vinyl chloride, acetaldehyde, that can then be converted downstream into useful products to support modern society. But this process has some disadvantages. It's energy intensive to convert calcium carbide to acetylene. And so what happened was in the coal producing region of Germany, a new plant came online that was able to a new refinery came online that was able to produce large quantities of ethylene. And so naturally people started asking, could we get access to these same target compounds that we need, but rather than doing it from acetaldehyde, from ethylene. And so from that simple question, a whole field was born. And so this problem of how to convert ethylene to value-added products was taken up by a company called Wacker Chemie. One of the lead scientists on the project was the gentleman shown here, Walter Hafner. And the reaction that he envisioned was one where he would take ethylene in the presence of O2 and some catalyst. And the first one, or some of the early ones he tested, were these palladium on carbon heterogeneous catalysts. And he was hoping to get out an epoxide. And if you are up to speed on modern organometallic chemistry, you might think this looks like a very bizarre reaction. And I would agree, this looks like a bizarre thing. You know, this probably isn't what you'd predict would happen, but they didn't really know the rules of the field. They were writing the rules of the field at that time. So they ran this experiment. And you can imagine this happening in like a big reactor. And as the story goes, when they opened the reactor, they immediately knew this was not what they made because they had a very distinct odor. And if you've ever smelled this compound, you know what I mean. A very distinct odor that they knew immediately that they had made acetaldehyde. And we'll talk about mechanistically how this is done and how it connects to what my group does in a minute. But actually, this built on a previous observation from even earlier, 50 years before. And it was known back then that people would use palladium dichloride, and they would use it as a test for if some random molecule, like let's say you have extracts from a tree or some leaves that were used for ethnobotanical medicines. You wanted to know what the structure was, and you wanted to see if that had an alkene in it. You would treat it with palladium chloride, and if the solution went black, indicating precipitation of palladium black nanoparticles, then you would know that that molecule did have an alkene because this same process was going on. So I'll now fast forward through about 10 years of industrial development research where they were able to, Wacker Chemie and then others were able to render this process catalytic. So ethylene could be converted to acetaldehyde. This is a redox process. So in doing this, ethylene and water are converted to acetaldehyde. This process is oxidative at the alkene. So the metal, transition metal catalyst, palladium-2, needs to be reduced to palladium-0. And then one of the key innovations was that they were able to couple this redox event with a copper-1,2 redox event that can be turned over by molecular oxygen. So you have this dual catalytic process, but in the end, it's this beautiful transformation where you take ethylene, you make acetaldehyde, and the only chemical inputs basically are O2 and water. It really doesn't get any cleaner than this in terms of green chemistry principles. And so then this process was developed for actual commercial production. There are a number of engineering advances that I won't bore you with those details. Sorry if you're a chemical engineer, but this process then became a commercially viable way to make acetaldehyde, and actually was the first commercial application of catalytic organometallic chemistry, setting the stage for developments like modern cross-couplings, et cetera. This is what the journal format looks like in the 1950s for Angewandte Chemie. This is the first report of this reaction, and you can see some of the key steps depicted here. Now, in terms of organic synthesis, normally I don't know what fraction of the audience works in organic synthesis labs, but normally, we're trying to work with molecules, starting materials and products that are more complicated than ethylene and acetaldehyde. So a laboratory scale version of this transformation was then later developed that can take alkenes that are more commonly encountered in the course of academic research, things like dodecene or hexene, and convert those into methyl ketones. So this is known as the Suji-Wacker, where the Suji group made this modification of running the reaction in DMF to do this on laboratory scale. And the reaction proceeds with reliable Markovnikov selectivity, meaning that water is introduced at the more substituted of the two, the oxygen atom is introduced at the more substituted of the two carbon atoms. And this activation mode, which will become, if it's not clear now, will become clear in a minute, where the palladium-2 catalyst can bind to the alkene and promote nucleophilic addition, turns out to be general. It's not just restricted to water, or we wouldn't be having this seminar. It also works with things like nitrogen nucleophiles. So in this case, phthalimide as the nucleophile can engage the alkene. And then you have the analogous type of process, but in this case, you're making an enamide as the product. This was work from the lab of Shannon Stahl in the development of a catalytic AZA, so-called AZA-Wacker process. So here's a general depiction of the catalytic cycle for this process. Palladium-2 coordinates to the alkene. As I said, this triggers polarity inversion. The alkene becomes electrophilic, and that can enable the otherwise weak nucleophile water to attack. That forms the carbon-oxygen bond and the carbon-palladium bond. Now, this next step is very strange if you thinking in terms of main group chemistry, but turns out to be pretty common in the organometallic literature, which is that in the presence of a hydrogen atom that is beta to the metal, so this carbon is alpha, this carbon is beta, a process called beta hydride elimination takes place. And this is very fast, typically, because it is intramolecular, and because this metal is not at all conformationally constrained. So you can imagine it's rotating around and then it pairs up with its hydrogen atom and it is lost as palladium hydride. In so doing, the organic substrate is now oxidized first to I've depicted it here as the enol tautomer, but then eventually it will form the ketone. And then this palladium hydride it is ultimately reacts with the oxidant to regenerate the parent palladium-2 in terms of how the overall catalytic cycle looks like. But if we want to develop a very general 1,2 difunctionalization, then this process of beta hydrogen elimination is going to be a problem, because this is like the rapid ejection seat of the metal from the organic substrate. So we need to find a way to suppress this if we want to do difunctionalization. So we have a number of components of what we want to accomplish, but also I think hopefully it's evident what the challenges would be for how to develop these types of difunctionalizations. One that I didn't mention explicitly, but maybe you've already inferred that this is going to be a problem, is how to control which of the two carbon atoms is engaged by the nucleophile when we move away from simple terminal alkenes and, for example, move to internal alkenes. Now you have two potential reaction sites. The stability of the corresponding carbocations is not so different. So how are you going to differentiate between those two potential transition states? And if you cannot differentiate, you're going to have poor regiochemical selectivity. This problem is specifically the one I alluded to on the previous slide, where after you form this adduct, where the nucleophile has engaged the alkene, now the metal, if there's a beta hydrogen atom present, then that process is going to be fast, and that will be the end of the show for your difunctionalization. And then you also have this problem, and hopefully everybody in the audience can appreciate this, is what you're trying to do is a 3-component coupling. One of your coupling partners is a nucleophile, one of your coupling partners is going to be an electrophile, and you have an alkene in solution. And the nucleophile and electrophile, by very definition, want to react with one another inherently. And in fact, the catalyst that you're trying to use can also promote those two reacting directly with one another. So you need to have the kinetics of your desired sequence of events be such that only that sequence of events is happening and not a bunch of other things that could happen in solution. This is like, you know, like if you're, you know, if you go to like a big house party and you're trying to get, you know, 3 people to talk to one another and only one another, but the dance floor gets too out of control, everything is going to get jumbled up like a mess. So you sort of need some separate room where you can keep the 3 people engaged in conversation while the party's going on. Okay, so the strategy we're going to use that we thought might work for this is called a substrate directivity approach, or in other words, a directing group approach. What that means is that we're going to look at alkene substrates that contain some Lewis basic functional group. So think here, carboxylic acid, alcohol, amine, that itself is capable of coordinating to the metal. And then that Lewis basic functional group we can either use in its native state, or if we need to, we can attach an auxiliary group, meaning some type of like molecular scaffolding that we will only put there temporarily just for the purposes of doing the reaction, and then we can remove it later. But that scaffolding could have even more Lewis basic sites, so it could coordinate bidentate, tridentate to the metal, et cetera. And the key point is that initial coordination between the Lewis basic sites is going to choreograph or template all of the downstream elementary steps. So it will allow us to control regioselectivity in the nucleophile addition step. Then when we make this intermediate, now it's cyclic. So it is conformationally restricted. It cannot quickly undergo beta hydride elimination like I talked about before. It's locked in. But it nevertheless possesses sufficient reactivity to be able to engage with the electrophilic component in solution. This also provides a nice handle for tuning the kinetics of all the different steps. So for example, if this step is fast, then the resting state of the cycle could be here, and this would then be a way of preventing your off-target, undesired nucleophile, electrophile 2-component coupling. So that's the general idea. And these types of metallocyclic intermediates they look maybe a little bizarre, but in the literature before we had even started in our lab, people had shown that you can make these types of intermediates by CH activation, cleavage of a CH bond by palladium-2, and that they're so stable, sometimes you can even purify them on a silica gel column. So these intermediates, the ones I'm drawing here and here, they do have some precedence in the literature. So this is not a completely off the wall idea. Okay, so here's our proposal for how we wanted to get started in developing difunctionalization. We actually simplified the problem. So rather than work immediately on these challenging difunctionalizations, we want to work on a special type of difunctionalization where one of the functional groups we introduce is just a hydrogen atom. And that makes things simple for reasons I'll talk about shortly. So we want to get at general difunctionalization, and our starting point is going to be hydrofunctionalization, where we're just introducing a proton as one of the functional groups. So here's the classical Walker or Asa-Walker reaction. We just talked about that in some depth. Now the question, with a directing group, can we derail the classical Walker so we can control regioselectivity in this first step, and then from the Pallada cycle intermediate, have an elementary step called proto-depalidation outcompete beta hydride elimination? That's the research question, essentially, the hypothesis that guided the experiments that I'll show shortly. And then the next thing to do is come up with a model system. So this is the first PhD student who joined my group, Jan Gurek, and I'll show you here is like the first 2 months of his research experiences in my group when he joined in 2015. So this is the model system that we designed. We have an alkene, and the alkene is not particularly activated because it's not in conjugation with any electron withdrawing functional group. But we have a carboxylic acid hanging 1 methylene spacer away, and then we convert the carboxylic acid to these amides that I'm going to show that have multiple Lewis basic sites for catalyst binding. And the transformation that we want to do is an anti-Markovnikov hydroamination, where the nitrogen nucleophile engages, and then we generate an organopalladium intermediate, and that organopalladium intermediate we then react with the proton. So based on literature precedents, we appended all of these different amide groups that can coordinate either monodentate, bidentate, and then we start assaying, do any of these actually promote the reaction? And it turns out this one, which is an 8-aminoquinoline, which I'll abbreviate as AQ, this promotes the reaction, albeit only in 16% yield. But this was a pretty good day in the lab because this shows that the overall hypothesis has some legs. And then we got to thinking, why is this only 16% yield? How could we improve it? And one of the conclusions that we came to, or hypotheses that we generated, was that if we think about how the proto-depalidation step happens, how to replace the carbon-palladium bond with the carbon-H bond, one possible transition state based on the literature is this 6-member transition state shown here, where in principle a carboxylic acid might promote this transfer. And so based on that hypothesis, we tested a number of different carboxylic acids. This is the one we found that works out the best, benzoic acid. And in a very beautiful series of experiments, John found that just adding more benzoic acid improves the yield from what I showed before in the low teens to now up to about 50%. Then we can play a few more tricks, just running the reaction at higher concentration to provide more thermodynamic driving force. And we can get essentially quantitative yield of the anti-Markovnikov hydroaminated product. And then John teamed up with a postdoc in the group, the first postdoc ever to join my group, Kin Yang, who's now a medicinal chemist at Gilead in the Bay Area. John is a process chemist on the East Coast at Bristol Myers Squibb. Together, they evaluated the scope of the reaction. They looked at the nitrogen nucleophile scope, and they found that relatively unactivated nucleophiles, so non-basic amines like succinimide, phthalimide, tetrachlorothalamide, these all work reasonably well. We can use coupling partners like Bach-amine. This is very convenient because the Bach group can be conveniently deprotected by TFA. And then Kin took the lead on looking at the scope on the alkene side. So he added substituents, for example, to the alpha position to ask what effect does that have on reactivity, and this is pretty well tolerated. When we add 2 different groups in the form of this gem dimethyl, now the reaction rate slows and you have to run the reaction for longer, and even still you get lower yield. One of the highlights is that we can do internal alkenes with very high regioselectivity and good yields. As I mentioned before, this is, at the outset, we thought this would be a challenging class of coupling partners because the 2 alkenyl carbon atoms are not well differentiated electronically. But through substrate directivity, we're able to do that and do them with quite high selectivity. One of the things that I personally love, and I think my lab loves, is understanding reaction mechanisms. And one of the tools that we use to do that is by characterizing organometallic complexes that are potential intermediates in our catalytic cycle. And we can use different characterization techniques like NMR, but my favorite is X-ray crystallography, because that allows you, just like I mentioned in my undergraduate research, I love the idea of seeing molecules with your own 2 eyes. X-ray crystallography allows you to do that. So here's what our catalytic cycle looks like, and I'll show you how we're able to get X-ray crystal structures of all the key intermediates. So first, the substrate binds to the metal. As I said, the directing group here, it coordinates in a bidentate fashion, and then the alkene occupies a third coordination site on the metal, and we can get a crystal structure of that and confirm that's indeed how it's coordinating. Then we add the nitrogen nucleophile, which attacks the terminal position. And actually then, because it has these Lewis basic carbonyls, it wraps back around and coordinates. So now all 4 sites around the square plane of palladium-2 are occupied, and we can get a crystal structure of that intermediate. And then if we treat this with a proton, we convert the carbon palladium bond to a carbon H bond. And even in this case, the product bound palladium complex, we can also isolate, but in the solid state, at least, it exists as a dimeric structure. This is probably not super relevant to catalysis, but this is what it exists like in the solid state. And we can even characterize this intermediate. So now we've really established all of the key intermediates in the catalytic cycle unambiguously through X-ray crystallography. And this provides a firm foundation for taking the next conceptual leap forward, which all along was to try to do difunctionalization. So how do we do that? Now the key is that instead of a proton as the electrophile, we want to have a carbon-based electrophile. And the target transformation was what's called a carboamination transform. So I won't talk about all the reaction development here. The idea is very similar. We use the same type of substrate. The key was in optimizing these reaction conditions. But the upshot is that we were able to develop this 3-component carboamination. And now this provides a very convenient way to make substituted gamma amino acids. So here's the embedded amino acid motif, alpha, beta, gamma amino acids with different substitution patterns. And these are valuable because it's a substructure commonly found in human medicines, including Lyrica. So we're able to prepare, as I'll show you, Lyrica and analogs thereof using this chemistry. It also turns out that these types of nitrogen nucleophiles are also quite common as medicine. So here's an immunomodulatory compound, thalidomide, which has a rich history in the context of organic stereochemistry, which you may have learned about in class. And we can use these as nucleophiles and carry out this late stage modification of existing drug compounds. Here's one exciting application of this chemistry where we can take one alkene starting material, one nitrogen nucleophile, and then we vary the electrophile that we use, and then how we work up the reaction, how we, the order in which we remove the directing group and cyclize or not cyclize. And this allows us to make 4 drug compounds in a very concise way. So as you can imagine, I mean, in our group, we're not necessarily motivated by translational chemistry. We're motivated by intellectual curiosity. But if you have the opportunity to advance biomedical research through your technology, then of course then you're going to be happy along 2 different axes. So this is hopefully foreshadowing how chemists may soon one day adopt this chemistry in the context of drug discovery programs. We would certainly love to see that, and we've seen pharma companies already expressing a lot of interest in using some of this chemistry. So where we've gone from there is to really try to build out this toolkit. As I said, the dream from day one was any 2 functional groups that we want with Mr. Potato Head level control. And we're not there yet, but we are getting there. So we've been able to add, for example, an aryl group and a boron group. Here's adding 2 different carbon-based functional groups, carbon nucleophile, carbon electrophile. We can do these reactions now in an enantioselective fashion through identification of a chiral ligand. And we've seen also that other groups around the world have picked up this approach, and now they're bringing their own creativity to the problem and introducing new coupling modules and new transformations that are beyond those that we would have even anticipated at the beginning of this research. So let me just show you one peek at what we're doing now, what we're doing most recently. So one application of this chemistry that is especially exciting in the context of drug discovery programs is when the nucleophile and the electrophile are actually tethered together, then this difunctionalization reaction actually closes a ring. Heterocyclic structures like the one shown here, it turns out are there are ways to make them, but those current technologies have limitations, and they're very much sought after in the biopharmaceutical industry. So this is now a slight twist on what I showed you before. Again, we have the substrate, the pi alkene palladium complex. We have a nucleopalladation event, but now we have this carbon electrophile tethered intramolecularly. It can undergo oxidative addition and reductive elimination. And now we've formed a ring from our alkene starting material. And so two students, or one student and one postdoc in the group, Huichi and Philippa, really developed this chemistry to great effect in collaboration with Pfizer, who are our close neighbors just across the street. We've worked for many years with their oncology medicinal chemistry team in developing these types of transformations that can be useful to them. So we can do these annulation, oxyannulation reactions to form benzofuran structures, to make indolin structures. In addition to forming 5-membered rings, we can form 6-membered rings. And this provides, as I mentioned, one-step access to these types of substructures, which are really prevalent in discovery programs. So I'll conclude here and make sure to leave some time for questions and discussion. And I'll just bring this back to, what really on paper is a simple idea. And I think, to me as a researcher, I think it's exciting when a simple idea on paper has a lot to it. That prompts you to unpack a lot over many years and continue to visit and revisit your initial assumptions and develop multiple iterations to address the problem. So this was really a simple looking transformation, but over 6+ years, we've grappled with how to control selectivity, how to prevent beta hydride elimination, how to develop coupling modules that can be stitched together with a high level of fidelity. And this continues to inspire us moving forward. I know that the audience has a number of undergraduates in it. And so I did want to, before wrapping up, I wanted to highlight opportunities. The first one I wanted to, at Scripps for research, and the first one I wanted to highlight is our SURF program, which we run every year. We have roughly 20 undergraduate students on our campus in California, and there are another 10 in Florida. The application is coming up soon. That's why I want to highlight it. You still probably just about have time if you're interested in applying this year. It's a great program, and a lot of our SURF alumni go on to our PhD program and other top PhD programs. The PhD program, I guess, would be relevant not only to the undergraduates, but the master's students in the audience. That program accepts applications every year. The 1st of December is the deadline. And one of the key points is, unlike every other graduate program in the country, there is no application fee. We want the best people, not the people who can pay for $100 for the application fee. And lastly, I just wanted to thank this wonderful team of coworkers. I tried to mention the names of key contributors as I went, but I'm really blessed to work with a talented team who's creative, hardworking, driven, and also just a lot of fun to work with. In addition to my human colleagues, I have one treasured canine colleague shown here, Hermione. She keeps us all in good spirits, and it's hard not to have a smile on your face when you're petting a fluff ball like this. And of course, in research, none of it is possible without folks to pay the bills. So we're grateful to be sponsored by both government agencies as well as several companies including companies that we collaborate closely with. And I would just say, if, don't be shy. Any questions you have now, I'm happy, of course, to answer them and to discuss. But if there's things that you just want to ask in private about chemistry or about life, then please do email me. My email address is right here. And if my name's pretty uncommon, so if you just search Keary Engle, you'll be able to find me online. Again, thanks to Zach and thanks to Garrick, and really looking forward to a discussion.
Wonderful. Thank you, Keary. Topic does not transfer very well virtually, unfortunately. First of all, I always love it when people include their dogs in presentation. It gives credibility to it all. So if there are any questions online, please jump in now and I'll open the floor up. I have a few questions, but just maybe to start things, I'll ask just one of them. I really like how you're coupling the mechanisms that you're mapping with crystallography to actually see if you're finding those structures that you're proposing as these intermediates as you move along. It obviously adds a lot of kind of credibility, or at least a tangibility to the mechanisms that you propose. I'm wondering if you couple this with kind of like Ken-Hauk type computational methods. In particular, it seems like when you're thinking about swapping out different ligands, different substituents that you might put on, it could really diversify the way you attack these things.
Yeah, it's a great comment, and
I guess it was more of a comment. Sorry.
well, comment / question. And yeah, so we do that. We work very closely. Well, we have one collaboration with Ken himself, but we've worked closely for about 5 years with one of Ken's former postdocs, Peng Lu, who's a professor at the University of Pittsburgh. And so we try to do this whenever we can convince him it's interesting, an interesting problem to look at. And as you said, the crystallography and MR characterization, that's one nice component. But when you can, I always love this triumvirate of fundamental organometallics, computational chemistry, and then the organic synthesis applications. So I think when we can merge all three is when we often get our best insights. So some of the things that we can ask using computational techniques are for example, what controls whether the nucleophile attacks like the backside of the palladium alkene complex, or whether it coordinates to the metal first and gets transferred inner sphere. Those types of questions you can't really get a satisfactory answer to through experimental techniques, at least the why part of it. And so computation is a great tool there.
Yeah, absolutely. Anybody else?
Actually, would you be able to go back to that slide where you have the crystal structures?
Sure.
Yeah, I'm just really quite interested. You had the acetate bridged complex. And of course, you can often have, mixed valence states. It looks like in this case here, you've got +2 in both, both here. Is that a particularly stable complex? I just find it, I've pursued a similar area that before, sort of trying to stabilize these. I'm just wondering what else you can do. Can you do redox chemistry to those to try and make mixed valence centers? Yeah,
so I think this is a pretty common, and you alluded to this, is a fairly common motif where you have like 2 palladium, like a bidentate ligand here, 2 palladiums, and then 2 bridging acetates, and something that looks, I have this drawn, our crystallographers draw this as a bond.
Lies, it's all lies, there's no bond there.
so we can debate whether we want to draw that as a bond or not a bond. But I think this is fairly common as long as the bidentate ligand here is pretty flat and rigid. I think when this is more 3-dimensional, you destabilize this, and this is not as commonly observed. So we, all of our data so far suggests that these types of intermediates, as they relate to catalysis, are probably off cycle. But there's work I'm sure you're familiar with from the likes of Tobias Ritter and
Yep.
Melanie Sanford, who've shown that similar types of intermediates accessed via CH activation can indeed undergo redox, and whether that's classified as a palladium 2 to palladium bis palladium 3 or palladium 2,2 to palladium 2,4 oxidation state was the topic of quite a bit of debate during my
Yeah, that was going to lead into my next question, which was, you know, when I was going through grad school, palladium 4 was sort of spoken only in hushed terms, sort of thing. You know, it was like lies, damned lies, and palladium 4 is a stable complex, sort of thing. But you know, there's been a lot of work since then, and you I think in one of your later ones, you have a nice palladium 4 center. I guess the question is I guess my major question is, do you see any off-cycle stuff that might suggest that there is other interesting chemistry that is perhaps happening, but maybe at lower levels than what you're actually looking for?
Yeah, I mean, to your first point, I think that, yeah, there was a quite a change in the like mid to late 2000s in terms of this kind of palladium 4 revolution. It had been proposed far earlier, and I think, you know, like well characterized in an organometallic sense by the likes of Canty and others. But then as it pertains to catalysis, that really only came online, you know, hot and heavy in the 2000s. So when, yeah, I alluded to this, and I did admittedly provided somewhat of a simplified picture, but in most 3-component couplings, there are a lot of other things that can and do happen, and so we observe other things happening in the flask in some of these transformations. I'll show this one for example. What's the best one? Maybe it would be clearer with the catalytic cycle here. So let me show this one. So as just one example, in this transformation, after you get here, then we want oxidative addition to happen, but you could also, I mean, we also already showed that from here, you can also get a proto-D palidation to happen as promoted by acetic acid, for instance. So sometimes we will see as a byproduct, the hydro-oxygenated byproduct. We sometimes will see also, depending on the reaction conditions, that this alkene, which as you can hopefully get a sense for, is a little bit precarious because it really thermodynamically wants to be in conjugation. If you're not judicious about choice of your reaction conditions, this can just isomerize into conjugation, and then that's the end of the road. It won't do any of the chemistry that I showed. It would just happily sit like that, or if anything, it will do Michael addition or polymerization or things like that. So I would just say, to answer your question in the most general terms, like at every stage, every elementary step, there are typically multiple things that could happen, and you know, we try to the best of our ability, we try to control the potential energy surface to bias it so only the things we want happen. But you know, sometimes we're not that smart, and so.
Thanks so much.
Of course.
I have a question.
Sure.
So in traditional cross coupling, usually the on-cycle catalyst is palladium 0. You guys seem to almost always use palladium 2 to start. I was wondering if that, since the metal's more electron deficient, does that cause the alkene to like donate more of its electron density to the metal, making it more activated for an outer sphere attack?
Yeah, couldn't have said it better myself. So let me try to pull up a slide that shows this, at least in general terms. I show here, at least in the palladium, that we've done a number of different, what we call redox manifolds or redox couples. So palladium 2,2, palladium 2,4. These are the two that I mostly talked about today, but you'll see that we've actually done the version that is more like a cross coupling. This is what you're talking about, palladium 0,2 couple, where the on cycle is palladium 0. The first step is oxidative addition to an aryl halide. And then what happens is you make a palladium 2 aryl. This would be clearer with a scheme, but I don't think I have one in this slide deck. Then that palladium 2 aryl can undergo a directed migratory insertion. And the key difference is then the aryl group is distal. So that's what's actually happening in this transformation I've shown here. And the reference is this one, if you're curious, the Angevante 2019, where we, from palladium 0 and an aryl triflate, we generate an aryl palladium 2 that undergoes migratory insertion and then transmetallation with B2 pin 2 and rectification. So you're right. I think when you palladium 2 is more piloacidic than palladium 0, and so these types of like NH bond additions, OH bond additions, those are typically going to happen at a palladium 2 alkene adduct. Aryl transfer can happen by different redox manifolds, including a 0,2 cycle as seen in cross couplings.
Okay, cool. Thank you.
Yep.
Well, we're a few minutes past 4. The undergraduates in the room are shaking their heads at me, so I don't have any more questions either. I want to thank you one more time, Keary. This was really interesting. I am disappointed that we weren't able to get you out here. I think that would have been a lot of fun, but I still really appreciate that you took time to do this and share some really cool, inspiring work with us. So one more time, thank you. And
Pleasure's all mine. Thanks so much for hosting me. And as I said, please do reach out over email if any questions come up.
Oh yeah, that's a good point. I do want to reiterate for just the undergrads. This is, these sorts of contacts are really powerful, and friendly people who are willing to engage in these conversations are really great connections. So please take advantage of this. All right. Thanks. Have a great weekend, everybody.
Thanks, Zach. Thanks, Gary. Thanks everyone for tuning in.
Yeah, no problem.